Today we're going to switch gear a little bit and talk about, again, some of the basic techniques in machine learning. The last two lectures, we had somewhat a shallow dive into deep learning. And in the next few lectures, we're going to have deep dive into the shallow learning, some of the learning mechanisms that we used in the past, but also are well understood in terms of their behavior. And they are very often revigorized, in recent years, to further enhance some of the advanced techniques in deep learning and so on, right? So today we're going to talk about what is known as the ensemble learning. Specifically, we will be covering a very famous algorithm known as boosting, okay, from the weak learners. So what is weak learner, right? So weak learner basically are simple algorithms, for machine learning, such as, a naive Bayes. You have heard about that already, I hope, and the logistic regression. So these are linear separation boundaries, like this one, right? You can basically just fit a line with unknown slope, and the intersection. Based on data, you figure those out, and then they basically help you to label the data. And sometimes it can be a decision tree in this case, which gives you a more complex boundary, but the mechanism are very, very simple. And depending on the level of the depth, it can still be a very weak learner. And there are some virtues of these weak learners, as I indicated from here. Usually, because of their weakness, they are known as to be low variance. What does that mean? Basically, they are not very, they're not very much easy to overfit data. They intend to be, fitting the larger trends, but not on every examples. Therefore, when you change the data, they don't change much. That's called low variance. But of course, on the flip side, they are also highly biased because they basically cannot really solve, a very hard problem. And if your data example have a very curvy and irregular boundary, these weak learners are not able to capture those nuances. Okay. So people thought in the past, can we, invent, the weak learner in a way that we leverage on their advantage, but avoid their weakness? Well, obviously, there are no free lunch in the world. Therefore, the obvious answer is no. But sometimes, if you really work hard on it, I'm going to show you an example. This, win-win scenario is possible. Okay, let's see how it happens. This is a very classical example. You probably can see also already from the example, where the inventor and where this algorithm come from, right? So here we are going to say do a sentence classification. Imagine the sentences from the calling center, and well, it is very, very ancient now, right? So nowadays we don't have a calling center for cell phones and asking for collect calls and for direct calls and so forth. But these are the norm, 20 years or maybe 30 years ago. Basically, when you make a long distance call, you can first call a calling center and place them, ask them to place you on, multiple categories, maybe two. Say you want the receiver to pay your call, or you will pay the call, right? So these are the two options. So how can I automate this algorithm or this process? Because in the good old days, there is an operator sitting there, who will be switching you to different channels. This is pretty expensive. So this algorithm was actually invented in one of the major providers, AT&T, by a famous researcher who used to work there. In fact, many of our nowadays famous researchers, including the deep learning pioneers like Yang Kuhn, was originally employed in AT&T and Bell Lab. You can imagine this is a hub for many of the modern innovations. And then they were trying to figure out what's the right rule, easy to implement, hopefully, and lightweight, but still, working effectively. One thing is to really find the so-called weak learners. The weak learner could be so weak that you just classify based on the frequency or even the instance of a keyword. For example, if you see the word card is mentioned by a caller, then most likely he is going to or she is going to ask for a collect call. Otherwise, she will pay him by herself, right? But obviously, this is inadequate because there may be other words or maybe no specific keyword at all by itself to indicate intention. Therefore, it is very hard to find a single highly accurate predictive loop based on such a keyword. So then comes to a heuristic known as the voting mechanism. This is actually the precursor of a ensemble family of methods. So mechanism is very simple. You just, instead of one rules, you basically have one hypothesis which look at the word card, for example, and another hypothesis which look at another keyword, say collect, or pay or whatever, right? And then you are going to use each of such classifier to classify the incoming sentence. And then you are going to now make a voting, to see how many, time among all these different classifiers, they vote the same or not. You can even, put a weight for each of the classifier based on maybe your guess or your experience of their competence, okay? And that basically makes your hypothesis in the end a weighted combination. And geometrically, this kind of a decision rule is not going to give you only a linear surface, like you have plus and minus here. It may be a piecewise linear or some other fancier shaped decision boundaries, because you are combining them in different orientation. One is like this, the other is like this. Then you have more like a square rule or something like that. So that's the second step. And but then the issue comes, right? How can we learn such a thing automatically? Right? For example, how can I force each classifier or each simple weak learner to learn different parts, of the problem, say using different keywords? Because if you automatically learn it, what if they both choose to make decisions on the word card? Right? You need to somehow separate them. And now, of course, you need to figure out how to assign the weights. Okay, so this basically defines some of the early missions in ensemble learning. Then comes another algorithm called bagging, which is in spirit similar to a voting or maybe ensemble learning, but the approach was different just because of the way it was realized. Because in this case, the bagging algorithm was using the decision trees as a base learner. Well, decision trees, depending on the depth, can be weak and can be strong, can be too strong, to be flexible. Did we cover decision learning, by the way, Daniel, in the early lectures?
Yeah, we covered decision trees.
That's great. Yeah, so you know it very well. When you grow the depth decision tree into like a couple of steps or maybe even a dozen, then you can easily fit a lot of difficult data points in the training set to the point that you make no mistakes. But when you get a new data points, you are likely to misclassify them. And we're going to actually talk theoretically more in depth in the later part of the semester about overfitting. But I guess you know what I'm trying to get into, right? So overfitting is basically to make a too strong learner, which has a low bias on the training, but very high variance, on the hold-off data set. But what they do here is that I combine these multiple strong learners to kind of weaken them in terms of the bias by, again, maybe a weighted or unweighted combination, and so that you can achieve maybe a balance between bias and variance. Right. So this is actually a very interesting thing. You just start from a strong learner and then weaken them, but hopefully make them a little bit more adaptive. So that's what bagging algorithm is about. And obviously, there are some technical issues, which is how weak is good enough so that we still can have a good performance. And somehow there's also a dilemma because eventually, when you are training the whole algorithm like this, you want them to make smaller and smaller mistakes on the training data. But in here, it's a little bit artificial because each one of these component in the ensemble is already very small, may actually make no mistakes already. And how come when you are training one or more, they start to make mistakes and when to stop, right? It's a little bit artificial and unnatural that causing you to get into a dilemma where, how to balance, the variance and the bias in a more natural fashion, okay? So that's bagging algorithm. So this algorithm didn't go very far, honestly. Although it does reveal a lot of insight of the behavior of ensemble learning. Random forest is actually an effort, to remedy some of the problems in bagging. In here, we're not going to combine all the full traits like this in the previous algorithm. We're going to now generate some randomization, in the training. For example, in training each of these tree, okay, for each of these tree, we're going to slightly perturb the training data. For example, I can select randomly n features from a total of p features. What does feature mean? Well, in the text classification I just mentioned, it could be the number of keywords. Originally, your text only look at, in total, look at 100 keywords. Now you are going to select, say, 50 of them to train this tree, right? And next time you are going to train a randomly reselected subset of features. So that creates maybe a less tendency of low bias, right? And it could make the variance a little bit better and so forth. So these are tricks called random forests. But the spirit is the same. You basically need to make this combination at the end of the day. And also there is a nice analysis of this algorithm, which says that typically you want to set the number of features for each such component learner to be a square root of the total features. And then when you choose enough, you are likely to have a good coverage and also a balance of the variance and the bias. Okay, so with all this history, you can kind of get a sense about where we're going, right? We have some heuristic already combining either weak learners and strong learners into some kind of a destiny where they have a good balance. And hopefully, we want to have more nice properties, such as when you have a new data sets or when you train more, they are not going to go unilaterally or unidirectionally into overfitting, right? So you want to actually make them to automatically stop, for example, when they can no longer, improve, testing a training error, but still don't sacrifice the potential generation error on the testing error. Okay, so that leads us to the algorithm called boosting, which was proposed by Rob Shapiro. That's the inventor I just mentioned in AT&T. He later becomes a professor in Princeton. He was one of the early pioneers in computational learning theory. His proof actually opened up the way of many technology we later use to analyze the algorithm's behavior, bounds, and the guarantees, and so forth. Okay. I'm going to walk through the algorithm in multiple passes. First, at a very superficial level, just on the operation. And then I'm going to explain the mathematics behind some of the key ingredients you need to compute. And then we're going to analyze theoretically some of the behaviors. And if you have questions, you can just raise your hand, and we're going to do live conversations. Okay. So the idea is that you want to start with a weak learner, and you want to train it multiple times on the data, and then learn a classifier that you can use it to vote or to linear combination. And we're going to just choose one type of classifier to make things simple. It could be a weak classifier such as a decision boundary, but later on, people invented techniques to make the component learner more and more complex. Of course, as an ensemble, they can become even more and more powerful. Then in each iteration, here is the idea. You are going to now augment the data a little bit. Okay, you are going to now weight every training examples by how difficult they are. Okay, I'm going to show you an example later on. You want to train yourself harder on the difficult examples and ignore more or less those examples that are easily classifiable. That makes in every iteration, a slightly different repurposing of the training process. And this weight will, of course, be changing, will be reweighted, adjusted during the iteration in every T. And this leads you to a weak hypothesis called H of T in every iteration. And then you are also going to somehow compute a weight, a strength of the hypothesis, okay, based on the current performance of that hypothesis. And then at the end of the day, you make a weighted combination of all these weak learners, and then you are going to make a decision, based on the total outcome. Okay, this algorithm, heuristically or operationally appears to be very simple, but there are a few key differences compared to the one I just mentioned. Okay, it is a weak learner, and it is now augmenting data, and also it is computing the weights not in a fixed fashion. It is evolving, based on the performance in every iteration. So now let's see what are the key difficulty issues, right? So here are some of the key issues. What is the criterion to optimize? Okay, you need to choose a loss function mathematically explicit so that at every iteration, this weak learner in here can be explicitly trained, right? And then how to estimate, of course, all these numbers, weights and so forth. Okay, so now having said that, here is a literal kind of pseudocode of that algorithm. You begin with n labeled examples, okay? And you are going to start with a base learner where the theta, this guy, is to be figured out. You can imagine this is a logistic regression that you learned earlier, where the weights are to be figured out. And then you initialize your first iteration in the following way. You are going to assign every example just the 1/n weight, so that the weights sum to 1. Okay. And then in every iteration from 1 to t, you do the following. You are going to now train the base learner on these weighted examples, or how to train them on weighted example. There are multiple tricks, right? You can just treat the data set, each data point as unweighted, but then you score the error, by multiplying with a weight. That's one way. The other could be you start from a totally unweighted example set, and then you sample the data, from that set using these weights, so that you create a subdata set. These are all, there are multiple different tricks that you can play. But at the end of the day, you are going to now learn this hypothesis basically by estimating the theta star, which is the estimator, the best estimator. It could be maximum likelihood estimator, or minimizing root mean square, square errors, and so forth. It's a black box that you can use. And then you are going to now compute the total error of this hypothesis T. Okay, I'm going to show you the equation. And then you are going to use that to compute the hypothesis weight. And then you're going to now update, the weights of every example based on this new classifier, because, it's updated on the classifier side. Therefore, the difficulties of example should change accordingly. And then in our next round, you are prepared to retrain it. And then you output this whole thing. I have a question here. Is the slide seems to be missing from the hand? Don't worry about the handouts. You can follow exactly from here because there are some redundancy in the handouts, which I choose to skip. You can just focus here. Yeah. It's in the slides, but I didn't show it. Okay. The second question. Okay, fine. Okay, so now let's, oh, I'm sorry. Here I have some, I didn't check this is sigma, and this is alpha k. I'm going to make it more beautiful next time by looking at, okay. All right, so here is how you compute the key quantities I just mentioned, right? For every, round, in the k iteration, I compute a sigma k equals to, now you can see the weighted sum of errors. This I of y and h is basically just here. Sorry for missing all these symbols. Hopefully in the handout you see it, right? So this I function is what you count on the classification error. And then this wi of k minus 1 is the weight of this example in the k minus 1 iteration, basically previous iteration, and also on this particular example I. Okay, so that's basically the weighted example based on your classifier experience so far. And then they will be, of course, normalized. So this is basically the total error of this particular round k. Having that, you are going to now compute the alpha k, which is the weight of this whole classifier that you just obtained. Okay, so basically this classifier. Okay, you can see it's just a log of the error ratio 1 minus sigma divided by sigma by theta, right? It's just a measure of the goodness of this. Sometimes it's also known as the cross entropy. And then you are going to now update your weights. And this weight is the update is also very straightforward. You have the old weights multiplied by now a exponentiated loss of due to the new classifiers, right? So remember, this is y type y multiplied by h is basically indicating whether you classify correctly or not, right? Because y is a plus and y sign, and h is a plus 1. If they agree, they will generate you a 1. If they disagree, it will generate a minus 1. And then I put a alpha, the weights, to reweight it. So that gives you the new kind of weights of every example. Make sure you are not confused. We have two weights now. This is the weight for the classifier, and this is the weight for every example in this iteration. And we're going to refresh it in every iteration for every example, okay? All right, so how does it look like in practice? So here is the animation. Imagine you begin with this example where I have just two type of labels. And you are going to just learn a very weak learner. It doesn't have to be very good. You learn this, or this weak learner isn't doing so well, right? It basically makes 3 mistakes. This one, and that one. And otherwise it was correct. And we are going to now compute the mistake and also the weight of this classifier. Well, the weight is not very high because it's not doing very well, right? We have only 0.42. Okay, as a result, the example gets reweighted. You can see that these 3 examples were mistaken, right? So they are considered to be harder examples. These other ones who are correctly classified are considered the easier examples. Therefore, we add more weights to these 3 guys, and the other guys are downweighted. Okay, now you retrain a classifier based on this newly weighted data set. And you can imagine where it should appear, right? Now I'm getting here, which is working really hard to get these three examples correct, but of course pay a cost that these three guys are wrongly classified. But they are going to cause smaller damage because now these examples are lower weighted than the first round. Okay, you've got a new classifier, and you can see this weights is greater than this one, just to capture the dynamics. And then with these two things in together, that basically causes a nonlinear classifier already. If you consider the weighted sum of these two boundaries, right? It's almost like a box kind of classifier that somewhere in the middle will take certain sign and somewhere outside will take other sign. Then accordingly, you are going to reweight the examples. And now these three guys gets now higher weighted, right? And then I learn another classifier like this, okay? And if now you consider a combination, a weighted combination of these three classifiers, you actually get something like this, okay? Which gives you not just even a box classifier, but a, I don't know how to describe the shape. It's a irregular classifier with piecewise linear boundaries, and which gets actually all the example perfectly labeled now, okay? So this is just the whole idea. It's very, very straightforward, very intuitive. We call each of these line, this weak learner, a decision stump, and they are usually very, very easy to train, in every iteration. Therefore, the cost was very, very marginal. But still, you can get high performance. And hopefully, this one won't be too much overfitting, meaning that by having more examples in, you are not likely to overfit, because it is not like finding a curve like this, literally going like that. That probably is a little bit too risky. But how to achieve that automatically, right? Why we actually end up with this algorithm. So now let's see some kind of a design principles. For example, why our updated equation are taking all this very funny form, right? Are these equations just out of a imagination, or there are some fundamental principles behind their design? Since the third learner was the highest weighted, shouldn't it get to the classifier? Let me see. No, I'm going to read out the question. The question says that since the third learner was the highest weighted, shouldn't it go to classify the right corner blue? Let's see. You are saying why right up corner blue, this one? It could. That's why it is labeled as a mistake. Yeah. And also it's higher weights. Yeah. As someone is answering that already. Yeah. All right. So let's look at a little bit more. So actually, this is a good exercise for myself. I need to now reinvent all the equations I wrote a couple of times ago. Let's see. Typically, the measurement of error is called a loss function, right? And there are different ways of designing loss function. We call, maybe let's give a name, loss function of the training label versus the hypothesis, right? And here we have already seen one loss function, which is just the delta function that you match or mismatch, right? And then there is also something called a generation error, which actually measures the quality of, in terms of variance and also testing error, which can be designed as this. This expectation is on the whole data set they are going to see in the future. And therefore, you are counting basically the classification error of new data, using the current classifier, right? And we want to, of course, find AH, not just fitting on the training data, but also doing well on this generation error. And here is a formula, how to minimize. Usually, the generation error can be replaced by, an empirical error. The sum can be, the expectation can be replaced by a sum of all these errors. But the boosting idea I just described is to start from first minimizing what we call the empirical error, which is literally just the counting of all the errors. I'm sorry for this, but your handout should be very clean here. Counting of all the empirical, all the errors on training examples. That's why it is sum over 1 to n, I equals to 1 to n, and then divided by n. We're going to try minimizing this in typical learning algorithms. So in here, we're going to try something else. Remember that this particular algorithm has some deficiencies. It is not a smooth function that you can easily differentiate. Therefore, you cannot really come up with a nice, clean algorithm to update the parameters in this function, which is the theta weights. Okay, so this is a typical problem in machine learning. Your kind of desire is to minimize discrete error, but your computing procedure prefers a smooth, continuous kind of error function. So here is just a remedy for that. We're going to now turn the empirical loss into what we call a exponential loss. Okay, so this is how it looks like. Okay, just exponentiate the product of the label and also the prediction. And then, do I have a minus sign here or not? I forgot. Yeah, it's a zero loss. Someone asking that, yes. Okay, so this is known as the exponential loss. Okay, and our goal is to now really see what we can do, when we minimize, the exponential loss over free parameters, which are the theta, basically, in the classifier. So let me reproduce all this. I think I'm missing a alpha here, right? It should be alpha.
No, there's no alpha there.
There's no alpha there?
No.
Oh yeah, there's no alpha because the alpha is in here. Sorry. So this h of m is the classifier in the mth iteration. Okay, and as I said, we have a weighted combination of the weak learners from the previous m-1 steps, right? Or m steps, until now, yeah. So the decision hypothesis at this step is now set to be the weighted combination of this. Okay, so now let's plug them in. We're going to have the alpha 1 and so forth. Okay, like this. Okay, straightforward. And then let me do some algebraic trick to rearrange it. I'm going to take out what we call h of m-1, basically the hypothesis from the previous iteration, which was made up of m-1 decision stumps. Okay. Okay, and obviously you can see from here, this basically is like a chopping, a part that is just ahead of the last decision bound stump. I'm really sorry.
Can I ask a question, Professor?
Okay.
Yeah, so in your slide, I don't believe the second formula has an alpha 1 on it. It should be an alpha 1 there, right? But on the slide, there's actually not. The second line.
Oh, okay. I don't have it. Then you can plug in. Yeah, there should be.
Yes, okay. Cool, thanks.
Okay, yeah. So now the whole thing falls into two parts. We're going to now rewrite the first 1-1 decision stumps into just one thing, which is in here. And then we're going to now carve out the last piece in here into here. Sorry, this is looking ugly, but hopefully you get my idea. We're not making basically a exponential of a sum of n terms, m terms into now a product of two terms. The first term is basically this m-1 classifier, and then the last term is the new one. Okay. And then I basically just define such a thing, weight, because this particular term is defined on every example and then indexed by m, which is the iteration. So basically, we call them the weight of the I example in the m-1 iteration. Okay, that's the weight. And then this one, is basically the new loss, augmented loss, from the new classifier. Okay, so that's why you see the W was defined in this way in the previous slides. It's basically coming from, a factorization of our exponential loss in the training process. Okay, so in sum, what's happening is that you combine classifier based on the M1 minus 1 iterations. They define a weight loss criteria for the next kind of a simple classifier to use. Okay, and then you are going to use them to weight each examples, and this can be called something like a classifiability or difficulty, as I mentioned earlier. All right, now we are going to, in fact, the nice thing is that we see a symbolic separation of this new guy for the M's classifier versus the old guy, which are the older M-1 classifier. But now when you figure out this theta, it still becomes a little bit hairy. How do you optimize the theta, over this equation? Well, exponential makes everything coupled and the nonlinear. It makes the mathematics a little bit hairy. So one simplification was further introduced called the linearization.
Just before we move on, there's a question in the chat. Someone said, I think alpha I should not be there for the second formula on the previous page, because the final prediction, that's the final prediction after M-1 classifier. Maybe we should clarify that just to be sure.
Okay. Yeah. Thanks for you guys are great. You guys are have such a sharp eye. Yeah. So I apologize here. So this one is called the h of hat m-1. Yeah. So indeed, it is the ensemble already. Yeah. Depending on how I express this guy, if it is already an ensemble that is weighted sum, you just forget about the alpha. Here, because the symbols look broken in here, I was thinking I'm missing the entire sequence of just the explicit summation. And in that case, it's a weighted sum. But yeah, I guess you get what I mean already, whether there should be an alpha and should not be, depending on whether you already express them as a summation or it is already a post-summation summary of the ensemble, right? Any more questions before I move on? I want to make sure that you all get it. Super, okay. I can see that you are completely with me, which is very, very good. So let's move on. I just said there is another trick known as the linearization of the loss function. Basically, it says this exponential loss can be further expressed as using Taylor's expansion, for example, if the alpha is a small value, to be 1 minus this guy. Okay. Now the loss is turning from exponential loss into a linear loss, which of course is very easy to differentiate, right? And as a result, your empirical loss at this step becomes a little bit more friendly. My gosh, this is terrible that I am creating all these troubles. Next time, I promise I'm not going to make it again. Okay, so because of this linearization, when you plug it back to the empirical loss, now this guy and this guy becomes a little bit easier to lead to a factorized equation, okay, which is like this. The first term in the additive form, not a multiplicative form, is just the sum of all the earlier weights, okay? And then the later part, the second term, is now a term of this, which is a weighted sum of this very simple +1 - 1 loss times the sample weights and times the classifier weight. Okay, it's just an algebraic trick to make the whole equation easier to optimize, because now you have all these linear dependencies. And then it also makes it more explicit that this time we're going to only worry about this new component and forget about anything in the past. But in this equation, you have everything separated from the earlier history. There is no kind of involvement of the previous rounds of decision steps, except the weights that it is determined from the previous classifier. Okay, so that basically leads you to a possible algorithm. At M stage, we're going to now just optimize the theta star, by optimizing this particular term. Okay, and leave the alpha out, because they basically, after differentiation, they actually disappears from the entire optimization step in theta, right? Yeah, so decouples the theta, and the alpha is achieved by the linearization as well. Otherwise, you will be cross kind of coupling, the theta and alpha, which is also manageable, but it's making the whole process more hairy. Okay, so now you solve the solve the theta using the weighted examples as reflected in here. And then remember, we have a way to compute the sigma of k, right? Which are the total weighted error that you made, on the training example. And then you're going to now use this formula to compute the alpha. And where does this formula come from? Well, it is coming from this particular equation. You actually now have this equation. And if you take a derivative of in fact, you don't have there's a closed form equation of the alpha once you plug in the optimum theta, which leads you to the classifiers. Okay, so now I summarize. There are three key quantities, in this AdaBoost algorithm. One is, the sigma alpha, sigma k, theta k of total error in kth iteration. The other is the alpha k of the weight of the classifier and at iteration k, and also the wi's of k, which is the weight of sample I at iteration k. And now you see all these equations, where they come from. It is all coming from the same source, which is the exponential empirical loss of the classification. Okay, it's a clean theory and mathematics. And then at the end of the day, you are going to combine all this, and you could do a cleanup by further kind of normalize, the alphas, so that they sum to 1, which makes some of the algebraic behavior even nicer. Okay, and then you're going to just keep going, on the M, going from 1 to say capital M, and then hopefully you will converge. So converge is also very interesting behavior. What do we mean by converge? In fact, I want to ask some students here, if you were now having this, when do you want to stop? You keep training new classifier, adding them back to the pool by this weighted equation, you reweight the example, you retrain another M+1 classifier, and so forth. When do you stop? When weights would not change a lot. You're right. Yeah, I was trying to set a trap for you, because I was, let me see, error is limited, or when new classifiers would give approximately the same results. Yeah, okay, the two questions I just read were falling into the trap, but still it's a very smart answer. The first one was actually quite insightful, or maybe having the right intuition. Now, just to repeat, I got 3 or 4 answers already. Some of them are saying the errors I made on examples won't change, say making no errors, for example. And then some others suggest that the weight, say for example, the alphas or maybe even the thetas stop changing. I would go the later, not the former, because it turns out that in this boosting algorithm, even if you stop making classification errors, okay, on the current version of the classifier, if you train again, you still have a chance to further improve. That's actually the magic of the boosting algorithm, as I'm going to show you in a second. All right, just to recap, we have now an algorithm called boosting, and basically it keeps sequentially adding new component classifiers, each trained on related examples. I really want you to take home this message. And the adder boost has a particular way of normalizing the examples, right? And that reflects the difficulty of the example in current classification version. There are a few free kind of knobs that you can tune. I want to mention that before I jump to the theory part. Following up the example, let's see, since the okay. Someone saying that does this restrict to only the +1 and -1 label of the classifier of the problem? Do we, for example, can we do multi-way classification? Good question. Yeah, I'm going to answer you in a second. These are all technical variations. Once you understand the principle, just like in your network, you switch the head of the bottom layer. You can turn a classifier into a multiplexer or some other things, right? In here, there's a way to do it, but I will mention that later. So you have a choice of base learner, and just now I choose a decision stump. You can actually have other base learners instead of arbitrary, from a wide collection, maybe not arbitrary, but many collections, multi-layer neural networks, a decision tree, and the radio-based function and so forth. So that's basically a plug-in, because when I talk about the procedure, I use a h of x and a theta. This h can be a lot from a lot of different choices. Okay, and how base learner operates on weighted example. If you recall, I just mentioned the 2 ways already. Right? One is to score the error. The other is to resample the data. There are many other trades. Maybe a combination of those is also fine. Okay, now goes to the stopping criteria I just mentioned. That's actually what's nice about Shapiro's fundamental breakthrough paper. He showed this graph, which shocked many of the researchers of that time. So he showed a training graph, which have this very strange mysterious bump, which says that it doesn't improve at all in the beginning, but drop afterwards. At the beginning, I think this one is explainable because it's a weak learner. Before you combine too many, it's still too weak. And sometimes when you just begin with the combination, it may make the things worse. So intuitively, this is reasonable, but you can keep doing that. So he kept doing that. And he reached to a point where the training error becomes 0. Okay, and when you have training error become 0 already, and for most algorithms, especially nowadays we train deep learning algorithm, the cycles are expensive, and you may be fighting with others for resource and that. So usually the temptation is that you will stop right after or soon after you see 0 in your training error. Right? What's happening to Rob's experiment is that he reached 0 pretty early, maybe less than 0 rounds. It's just too good for him to believe it's enough. So he would continue. In fact, he continued quite a bit. He continued another few hundred, if not thousands of iterations. And then he kept a holdout data set. He found this phenomenon that the testing error on the holdout data set keep dropping. Okay, even when you retrain the classifier on examples which you already make 0 mistakes. Okay, and then at the end of the day, they start to stop decreasing. Okay, so of course this makes a practical issue. Really, when do you stop? Because in real life, you don't have a hold off testing data set, or you split your training into testing and hold off, then you may still worry, what if some new data sets coming in, right? Should I still keep training or not? Because I may be platooning on the hold off, but still hoping to see the decrease of the generation error, right? So these are all legitimate doubts. I guess then the suggestion from one of the students just now will work. You basically monitor the alpha and the theta and keep training them and see, do they change or not? You ignore basically this sigma part, and not the sigma part, but the discrete counts of the error. You ignore that. You do this. Okay. So why this happened? This is actually the key. You know, why actually when we see a example, a classifier which already make zero empirical error, can still keep improving, on the testing data. Usually the experience from machine learning theorists was that if you are making zero error on the training data, you need to worry something else, which we know as overfitting. Are you already overfitting the data? You should actually not only stop right now, you should stop earlier. You should go back and make the whole thing a little bit weaker. Right? That's the kind of a traditional wisdom. In fact, here, the hypothesis or the theory also suggests that kind of a worry already, right? So here, you are going to see this again in my class of computational learning theory, but I want to just print it here because it's very intuitive to understand. Basically, whenever people learn a hypothesis H, and then you want to measure its error on the data set you haven't seen before, which is known now as the generation error. The error comes from two parts. One is known as the empirical error, the training error. You need to basically account for the error that you cannot overcome already on training error. Usually, if you use a decision boundary, no matter how you tweak the angle and the position, they will make some error on training, right? So this is a source of the error in the generalization. And then the other part is actually called the variance part, is actually due to the intrinsic complexity of the decision boundary or the decision hypothesis itself. It goes like square root of t, which is the number of iterations, and the d, which is the dimensionality of the model. Okay, we're going to know down the road VC dimensions and everything, which tells you how complex this model is. Right? The more complex the model is, the more likely you are going to overfit. And then M, of course, is the number of examples. The more sample, the better that you're going to reduce the risk. So at the end of the day, it leads to the so-called bias and the error and the variance trade-off. Right? When T is very small, you are going to have a large bias, but a small variance. Okay. But when you train T a lot, you are going to reduce the bias. Say this one will be reduced. You are going to fit the training data better and better, right? But you are going to now increase your risk of overfitting. So this is the traditional wisdom, and it's also well justified by the theory. Okay. But why we see this graph? This graph seems to be contradicting what just the theory predicts. Right? That's actually what I really like Rob and Yuval Freud's approach. They actually start to question the very way people analyze this error. Okay, and they actually suggest that this contradictory may justify a new way of analyzing the error based on different loss functions. Remember that in the original analysis, usually the rule of thumb of the error, this one, is typically defined to be the counting loss. How many mistakes that you make? You basically are committing a 0 and 1 kind of a hard mistake, right? Either you are wrong or right. And that actually leads to this analysis. But in the boosting algorithm, as we see earlier, you actually have a way to define not only the classification is right and wrong, but how right and how wrong. Okay, so this is reflected by the equation we use to make the classifier. Remember, our now mth classifier, or the classifier in the mth iteration is basically this weighted ensemble of weak learners, right? And then they will time basically the true label of the data. And this is obviously not a 0 and 1. It's not discrete. Okay, it is a continuous number between minus and the positive 1, right? So we call them the margin of the classifier. Okay. So if you treat this as a objective to minimize, which actually is captured in our exponential loss, you are actually optimizing a new kind of loss, which is known as the margin loss. And they went on and proved the guarantee of the margin loss. Okay, and they actually got a term where the generation error is actually dependent on this new margin loss, which looks like this. I'm not going to show you how to prove it because it's rather complex, but I give you this point of the paper. If you are interested in theory, you can read that. Right? In this new error term, over the margin loss, there is no t. T is gone. Okay, there is still a dependency of the dimension d. That's very intrinsic to the function you choose, and then the dependency on the data is also becoming a m of square, meaning that when you are using more data, you are going to have a stronger impact in reducing the variance. Okay, but in here we only probably care more about the dependency on t, because that means when you train more and more and more, it's not going to cause your model to overfit at all. It doesn't have any impact. The more the better, okay, as long as you can afford it. So that's a very, very kind of relieving message for practitioners, because you can focus on, for example, empirical stopping conditions like alpha, like theta, until you feel satisfied. And you don't have to worry about the overfitting part. The overfitting part is lying intrinsically in the model design, say how much dimension you need to accommodate in every model. But we're going to talk about that later. Okay, that comes to the summary. This is the boosting algorithm. It takes a weak learner and convert it into a strong one, right? And then it works asymptotically, minimizing the empirical error, but also it is avoiding overfitting, by maximizing the margin of the classification examples. Now, I have a question here. There is also a gamma term besides the m. Yeah. Okay. Gamma is what? I forgot. Yeah, let me leave it as of now. Oh yeah, the gamma is the general. Yeah, okay, I see. Gamma is in here. Yeah, sorry, I was mistaken. I was actually just puzzled why m cause a square. It's the gamma square. Right? So basically, it means that you can introduce this new error term as long as the gamma, the margin, can be further and further improved. The margin gets bigger and bigger. That means not only you are getting correct, you are getting more correct. Then it also will improve your performance on the holdout data set. Thanks for pointing that out. Yeah, it was actually indeed causing some red flag when I was lecturing. What are the error true and error train in the formula before? Okay, cool. Are you asking these slides? Yes, okay, yeah. Error true is what we call the generation error. It is the true error you are going to commit on a data set that you haven't seen before. Okay, it's a new data set for you. The error train is the error you actually committed on your training data set. Remember, I hope Ziv also covered, right? The way to do machine learning is that you are given a labeled data set, you train it to minimize the empirical error, and that's exactly this error. And then you are going to hope that when I deploy this algorithm to a new problem with a data newly coming I haven't seen before, I'm going to have low risk on error. And this risk is this part. Did I answer your question?
Can I clarify my question a little bit? So for the arrow true, is it the margin loss that you talked about, the margin-based loss? And for arrow train, we're using exponential loss to train it. So these
No,
are
no. In here,
like
the two are all
different
empirical
measures.
loss. It's not margin loss.
Arrow true is okay. Arrow true is like 0, 1 empirical loss, right?
Mm-hmm.
And then arrow train is exponential loss.
In here, in this equation, no, they are all empirical loss.
They're all empirical loss? Okay.
Yes. Yeah, they're all empirical loss. Because this is basically a measuring action, right? It's basically about exactly what you counted as a right and wrong. When we use the empirical, the exponential loss, that's the mechanism that we design mathematically for training. This is not the way we tell. It's like your backstage practice rather than the front stage performance.
Okay. And could you please explain the margin and the empirical losses relationship there? Are they like same?
Yeah. The empirical loss in here, remember, goes to 0 very quickly, right? Because it is a discrete loss, correct or right or wrong. The margin is a more kind of a mathematically nuanced way of telling you the strength of the evidence. For every example, for example, if you have a decision boundary in here, and here you can barely make things right. But if for something like this, then their margin is right. For example, in here, right?
Yeah.
For example, in here, I can create the same label with two different empirical loss. Here, the empirical loss is the margin loss is this big, right? But if I reorientate my surface, then the margin will be this big, right? And that means that this particular boundary is better than the other one.
Yeah, gotcha. It's more like the confidence. How confident are we? Yeah, gotcha. Thank you.
Yeah, precisely. And this particular equation helps to measure or quantify that kind of a margin. Okay. All right, all great questions. We've got a summary. We've got a few more minutes. That's a luxury that we can spare to talk about a few fancier issues, including the one raised in the class where, say, what if we have a more complex problem, say not a binary classification, right? So let's see. So I want to first maybe draw some analogy and the comparison of our boosting algorithm and the logistic regression algorithm just mathematically, just to show you kind of the principle or the art of picking the loss. You can see just now by switching from a binary discrete empirical loss to an exponential loss, you actually create a lot of nice impacts, right? In terms of the training, in terms of the generation error. So let's just review what are some other typical loss functions we use, right? So in logistic regression, we know that our loss is actually called is this, right? And then we are trying to combine this is basically describing the conditional probability of the label given the example using a sigmoid function, right? And then the actual loss is a logarithm of that, so we call this a log loss. And if you put the boosting and the logistic regression side by side, you actually will see a very interesting difference. So here is the log loss, but in boosting, it's minimizing a exponential loss, which is similar to in some way, because if I can show you, there's a shape in here. Exponential loss look like this, and the log loss look like this. They are both a smooth approximation to the step loss that we see in here. And as I said, this will cause the whole loss function to be differentiable over parameters. In this case, the parameters are the weights, which is the orientation of the decision surface. And here, it's the alpha and also the stuff inside the hypothesis, right? So that basically creates a mathematical convenience. And to side by side for you to remember, here, you see the contrast of the loss. And also you see the contrast of the decision surface, right? Here, it's a weighted sum of the input features, but it's just one set of the W weights. Okay, so this W weights is one set. In here, we have a linear combination alpha over all the H, and the H itself could be such a logistic regression function. Therefore, you have almost like a double hedge, that you have a lot more richness, in expressing nonlinear decision boundaries, just using linear basis. So it's not really more complicated, than this by too much. Okay. And then, of course, we learn the weights in here, and we learn the weights in here. Make sure you don't confuse. Okay, I think one thing that we want to remember in machine learning, that after you learn too many algorithms, you may get lost, about their counterparts. You may start to compare oranges with apples. In here, the alpha and the W here are not to be compared. Okay, the alpha are the weights of the hypothesis. The W here are the weights of the features. And inside every of the alpha T, which is the HT, you actually will have X data and also the weights. Sometimes we'll call them theta. Okay, so that's the relationship. And then, in terms of making decision, you can see that very often we make hard decisions using a sign function, but sometimes soft decisions gives you a way of defining either confidence or margin and so forth. And then you can also see that this soft kind of a decision boundary will really allow you to capture the effects of those outliers, right? So in here, outliers usually can play a role, in impacting, the orientation of decision services. They can really allow you to focus your attention on themselves, which are the so-called hard examples, right? So outlier is, in a sense, helpful, in allowing the decision hypothesis, to pay more attention, to the harder problem. Typically, in the logistic regression, you don't have too many kind of approach or mechanism to treat the outliers differently than other examples. In here, because of the sample reweighting, outliers do play a greater role than typical training algorithm. But they are also causing some troubles, because if you really have too many, outliers, it could dramatically increase the time to converge, and sometimes even fail to converge to a very compact kind of hypothesis. You may end up with having too many. Imagine that if you take a few tens of thousand steps to converge, that really means that the tens of thousands of linear decision services, and that creates a rather messy, hypothesis for you to port into a new problem. Right? Okay, so now lastly, I'm going to say just a few words about the extension, okay, which is known as the gradient boosting algorithm. This actually, the vanilla boosting, ADA boost algorithm nowadays are rarely used because, after all, it is based on a linear based learner. It is still very weak, especially in high dimensional problems where you want to classify an image rather than a word with a sentence with few words and so forth. And in those new problems, people start to introduce newer loss functions, such as the square loss, such as the logistic loss, and the margin loss directly, and maybe softmax loss and other things. So in here, the loss function is actually a black box, as long as it is differentiable and smooth. How many labels you have, and whether they are based on probability or based on margin is actually less of an issue. That's why you can actually plug in an entire deep neural network, as we said earlier, to be a base learner in a boosting algorithm. You can imagine an ensemble of deep learning algorithms, to do, I don't know, even more challenging things. Although nowadays few people do that because neural network itself is already a very rich type of functional approximators. If you recall, I mentioned that a 2-layer deep neural network, a deep neural network with 2 layers of hidden variables can approximate any real functions already. So with that level of richness, what you worry may be the overfitting part, but at least in terms of fitting the complex training data, you don't actually need to worry about any boosting algorithm. So people rarely boost the neural network. But down the road, I don't know, because many deep neural networks hasn't been systematically tested for their generation error yet. Okay, it's highly fitted to training data, and because of their expensiveness, it is very difficult to do systematic holdout experiment test. But that's an ongoing research. I'm not even sure whether boosting is the right approach to solve the variance and the variance trade-off over there. But that's how much I can say at this point. All right, I think that's the last page. We've got 5 more minutes to go. Any questions from the class? Here is one. It is a confidence of your classifier. I don't think it has a direct margin meaning in terms of, good point. Yeah, this so-called margin is abused, I have to say, by machine learning people. When you talk about, did we talk about the support vector machines already?
Yes.
Okay, yeah. So in SVM, very obviously the margin is literally a geometric margin, right? So in here, we are really talking about the margin being, as you said, the confidence of, in a statistical sense, or maybe in the even a psychological sense, the quality of the classification. You're right. But again, it is a continuous variable between minus and 0, 1. You can say more confident and less confident, or you can say that the margin of my correctness is bigger or small. Any other questions? Okay, if not, I will give back to you 5 minutes and I will see you next week. Thank you very much. Oh, by the way, I'm writing a lot of scripts on this slide. Do you want this dirty version as well in your review, or I'm going to discard all the writings?
Just one last question. In slide 33, so you wrote a proportional sign, and while the slide itself says, the handout has a plus sign.
Oh, a plus sign.
Yeah.
Okay. Yeah, you can see that's why lecturing out of the blue is out of the dark is very difficult. I think yeah, okay, I will correct that. Thanks.
So it should be a plus sign or a proportional sign?
I think it doesn't matter. It can be either way. It's when I say proportion, it's just suggesting some constants are missing, and basically this O is it depends on how you read the O meaning. But the follow what I originally typed, that's more rigorous. Here is more like an ad hoc.
Got it. Thank you.
Mm-hmm. All right. I will see you next week then. Bye.